Hello everyone. In this video we will be discussing about the basic processing unit. Let us first discuss about the fundamental concepts of control unit. Control unit is the part of computer central processing unit which directs the operation of the process. It was included as a part of von Neumann architecture by John von Neumann. It is the responsibility of the control unit to tell the computer's memory, arithmetic logic unit, and input and output device how to respond to the instructions that have been sent to the processor. It fetches internal instructions of the programs from the main memory to the processor instruction register, and based on this register's content, the control unit generates a control signal that supervises the execution of these instructions. A control unit works by receiving input information to which it converts into control signal, which are then sent to the central processor. The computer's processor then tells the attached hardware what operation to perform. The functions that a control unit performs are dependent on the type of central processing unit because the architecture of CPU varies from manufacturer to manufacturer. Example of devices that requires a control unit are control processing unit, graphic processing unit. Let us now discuss about the functions of control unit using control signal. The first thing is of sequencing. The control unit causes the CPU to step through a series of micro operation in a proper sequence based on the program being executed. For example, in order to carry out a task such as add, the control unit must generate a set of control signals in a predefined sequence governed by the hardware structure of the processing section. The control unit causes each micro operations to be performed, and the control signals are of two types. One is of external and other is of internal. The external control signal are nothing but of inputs indicating the state of the system, and the internal control signals are the logics required to perform the sequencing and execution function. So the input to the control unit are master clock, status info from the processing section, command signal from external agent, and the output produced by the control unit are signals that drive the processing section and responds to an external event. That is, operation is being completed or aborted is also being sent by means of the control unit. Due to the exception, there may occur overflow and underflow. This is also being indicated by means of the control unit. So the control unit undertakes the following responsibilities: instruction interpretation, that is reading an instruction, recognizing it, getting operands and route to appropriate functional units. Necessary control signals are being issued. The necessary control signals are being issued are for the instruction sequencing. The control unit determines the address of next instruction to be executed and load it to the program counter. The processor fetches one instruction at a time and performs the operation specified. The instructions are fetched from successive memory location until a branch or jump instruction is encountered. Now let us discuss about the connection between the CPU and memory. To execute a program, the processor fetches one instruction at a time and performs the operation specified. Instructions are fetched from successive memory location until a branch or a jump instruction is encountered. The processor keeps track of the address of memory location containing the next instruction to be fetched using the program counter. After fetching an instruction, the content of program counter are updated to point to the next instruction in the sequence. A branch instruction may load a different value into the program counter. Another key register in the processor is the instruction register. The instruction register, suppose each instruction comprises of 4 bytes and that it is stored in one memory word. To execute an instruction, the processor has to perform the following 3 steps. One is nothing but of fetch. So in this step, what it is going to do is it is going to fetch the content of memory location pointed out by PC. It is going to fetch the content of memory location pointed out by PC. The content of this location are interpreted as the instruction to be executed. Hence, they are loaded into the instruction register. Symbolically, this can be written as IR, which is being loaded with the content of PC. So assuming that the memory is a byte addressable, increment the content of PC by 4. That is, next the PC will be incremented as PC is equal to the content of PC plus 4. So carry out the action specified by the instruction in the instruction register. In case where an instruction occupies more than one word, this step 1 and this step 2, this is nothing but of step 2, must be repeated as many times as necessary to fetch the complete instruction. These two steps are usually referred as fetch phase, and step 3 constitute the execution phase. That is, step 3 is nothing but of carrying out the action specified by the instruction in the instruction register is nothing but of step 3, and that is nothing but of the execution phase, and step 1 and this step 2 are nothing but of the fetch phase. To study the operation in detail, we need to examine the internal organization of the processor. The main building block of the processor is being introduced here. We will start with a very simple organization. Later, we will get into the complex structure that provides high performance. The figure shows the organization in which the arithmetic logic unit and all other registers are interconnected via a single common bus. This bus is internal to the processor and should not be confused with the external bus that connects the processor to the memory and other IO devices. The data and address lines of external memory bus are shown in figure, which are being connected to the internal processor bus via the memory data register and the memory address register MDR and MAR respectively. The register MDR has 2 inputs and 2 outputs. The data may be loaded into MDR either from the memory bus or from the internal processor bus. The data stored in MDR may be placed on either bus. The input of MAR is connected to the internal bus and its output is connected to the external bus. The control line of the memory bus are connected to the instruction decoder. The control lines are being connected to the instruction decoder and control logic block. This unit is responsible for issuing the signals that control the operation of all units inside the processor and for interacting with the memory bus. The number and use of processor registers are not through Rn-1 vary considerably from one processor to another. Registers may be provided for general purpose use by the programmer. Some may be dedicated as special purpose register such as index register or stack pointer. Three registers Y, Z and temporary are being shown. Y, Z and temporary are being shown in the figure, right? So they are not being mentioned before. These registers are transparent to the programmer, that is, this is being, the programmer need to be concerned with the term because they are never being referred explicitly by any instructions. They are used by the processor for temporary storage during execution of some instructions. These registers are never used for storing or data generated by one instruction for later use by another instruction. The multiplexer MUX selects either the output of register Y or a constant value 4 to be provided as an input A of the ALU. The constant 4 is used to increment the content of program counter. We will refer to the two possible values of MUX control input selection as select 4 and select Y for selecting the constant 4 or register Y respectively. As instruction execution progress, data are transferred from one register to the other, often passing through the ALU to perform some arithmetic or logical operations. The instruction decoder and control logic unit is responsible for implementing the specification specified by the instruction loaded in the instruction register. The decoder generates the control signals needed to select the registers involved and direct the transfer of data. The register, the ALU and the interconnection buses are collectively referred as the data path. With few exceptions, an instruction can be executed by performing one or more of the following operation in some specified sequence. That is, transfer a word of data from one processor register to another or to the ALU. Perform an arithmetic or logical operation and store the result in the processor register. Fetch the content of a given memory location and load them into the processor register. Store a word of data from a processor register into a given memory location. We now consider in detail how each of this operation is implemented using a simple processing model. Instruction execution involves a sequence of steps in which data are transferred from one register to another. For each register, two control signals are used to place the content of the register on bus or to load the data on the bus into the register. This is represented symbolically in the figure. The input and output of register Ri and Ri out respectively. When Ri is being set to 1, the data on the bus are loaded into Ri. The data on the bus are loaded into Ri. Similarly, when Ri out is set to 1, the content of the register Ri is placed on the bus. The content of the register Ri is being placed on the bus. While Ri out is equal to 0, when Ri out is equal to 0, the bus can be used for transferring data from register. The bus is being used for transferring data from registers. right? When Ri in is being set to 1, the data on the bus are loaded into Ri. Similarly, when Ri out is set to 1, the content of register Ri are placed on the bus. When Ri out is equal to 0, the buses can be used for transferring the data from other register. Suppose that we wish to transfer the content of register R1 to R4, this can be accomplished as follows. That is, first enable the output of register. First enable the output of register R1. Output of register R1 by setting Ri out to 1. Ri out to 1. This places the content of R1 on the processor, right? Now enable the input register R4 by setting R4 in to 1. This loads the data from the processor bus to R4, right? So by means of which, if you want to transfer the content of register R1 to register R4, the processor will involve in this processing sequence. First, it will enable the output of register R1 by setting R1 out to 1. This places the content of R1 on the processor bus. Then it will enable the input of register R4 by setting R4 in is equal to 1. This loads the data from the processor bus into register 4, right? So all operations and data transfer within the processor takes place within time period defined by the processor clock. The control signals that governs a particular transfer are asserted at the start of the clock cycle. In our example, R1 out and R4 in are set to 1. The register consists of edge-triggered flip-flops. Hence, at the next active edge of the clock, the flip-flop that contains R4 will load the data present at their input. At the same time, the control signal R1 out and R4 in will return to 0. We will use this simple model of the timing of data transfer for the rest of this discussion, right? However, we should point out that other schemes are possible. For example, the data transfer may use both the rising and falling edge for clock. Also, when edge triggered flip-flop are not used, 2 or more clock signals may be needed to guarantee proper transfer of data. This is known as multi-phase clocking. An implementation of one bit of register Ri is shown in the figure. As an example, 2 input multiplexer is used to select the data applied to the input of edge triggered D flip-flop. When the control input Rin is equal to 1, when it is equal to 1, the multiplexer selects the data on the bus. The multiplexer selects the data on the bus. It will select the data on the bus. This data will be loaded into the flip-flop. So data will be loaded into the flip-flop. So this data will be loaded into the flip-flop at the rising edge of the clock signal. This data will be loaded only at the rising edge of the clock signal. When Ri is equal to 0, when Rin is equal to 0, then the multiplexer feedbacks the value currently stored in the flip-flop. It will feedback the value currently stored in the flip-flop. The Q output of the flip-flop is connected to the bus via a tri-state gate. When Ri out is equal to 0, the gate output is in high impedance state. This will be in high impedance state, right? That is electrically disconnected state. This corresponds to the open circuit state of the switch. So when R out is equal to 1, it is in high impedance state, and this corresponds to the open circuit state of the switch. When Ri out is equal to 1, the gate drives the bus, or that is, the gate drives the bus means the bus will be 0 or 1. That is, the gate drives the bus to 0 or 1 depending on the value of Q, that is output of the flip-flop. So that's all with today's discussion. We will discuss rest of the topic in the next video lecture. Thank you.